in the sectorial case. You have how many? Let me check. You have 50 minutes and 10 minutes for questions. You're welcome.
Thank you very much. My title of my talk was mentioned. Our group in Chelyabinsk State University study differential equations in Banach spaces with applications to partial differential equations, to initial boundary value problems for partial differential equations. In 2029, we obtained the grant of President of Russian Federation for leading scientific schools, and now we are working in the framework of this project. A class of fractional quasilinear equations. Briefly, I will talk about our general problems. If I recall, what is resolving a semigroup of operators for the differential equation? Let that is a Banach space. A is a linear closed operator, and we consider the Cauchy problem 2 for the differential equation 1. And as T is a resolving operator semigroup for equation 1, if family is strongly continuous with respect to T, S0 is identical operator, as T commutes with A, and such function is the solution of problem 1, 2. And we know that such family is a semigroup. It satisfies this equality. I recall the notion of fractional derivatives. The Riemann-Liouville fractional integral of an order delta is this convolution with power function. The Riemann-Liouville fractional derivative of the order alpha is defined by this equality. Here we need to take fractional integral and usual differential operator of the integer order m. M is this number. And we will use the denotation of fractional integral as fractional derivative with a negative order. And the Gerasimov-Caputo fractional derivative, for simplicity, it will be it is this expression. And I give the notion of resolving family of operators for fractional equation. Firstly, we saw this notion in the works of, for example, Emilia Bajlekova, but for similar equation, but with Gerasimov-Caputo derivative. We will consider only the equation with Riemann-Liouville derivative, and we have such initial conditions, M conditions. It corresponds to this number M. And as T is resolving family of operators, this family is strongly continuous. Operators commute with the operator A, and for all Z0, this function is a unique solution of this problem. Here we have arbitrary this value Z0 for the first condition and 0 conditions for other derivatives. And such conditions we call Cauchy type problem. Cauchy type problem, as in the monograph of Kilbas, for example, since they are Cauchy problem not for the function z, but for the fractional derivative, fractional integral of this function, fractional integral of the order m minus alpha. And such a family, generally speaking, has not semigroup property, and the general solution of general problem with arbitrary zk in all the solution, all the conditions, has this form. Here we have our resolving family and its fractional integer order integrals. And we see that fractional solution can be expressed through this family only. So here we have no semigroup property, but all other properties, all the possibilities of these constructions are saved, and we can use these operators. We can construct it in the explicit form and use them for study of such problems, not also linear, but quasi-linear. In our group, we study, for example, such equations, and we use a Cauchy problem if in the equation we use Gerasimov-Kaputov derivatives only, and Cauchy type problem if the derivatives are of Riemann-Liouville. And we can consider analogous equation, but with degenerate operator at the oldest derivative. And we can consider such equations, so-called multi-term linear equations, when the linear part of equation has several closed linear operators. And such situation, our participant of our group, Mikhail Turov, spoke about about such equations yesterday. And we can consider, he talked about the case when the derivatives are of Riemann-Liouville, and then we have Cauchy type problem, and then we have the so-called defect of the Cauchy type problem for equations with several Riemann-Liouville derivatives. But if the derivatives are of Gerasimov-Kaputov, then the Cauchy problem has no such troubles, and we can consider complete Cauchy problem. And such talk Ksenia Boyko gave 2 days ago. And we can consider also degenerate evolution equation of the same form, but with degenerate operator at the oldest derivative. And we can consider equations with distributed order derivative when we take Riemann-Stieltjes integral with respect to order of the fractional derivative. And if this derivative under the integral is of Gerasimov-Kaputov, then we can consider Cauchy problem, where the number of conditions defined by this upper limit of the integral. And we can consider special initial problem if here we use Riemann-Liouville derivative. And we can consider degenerate derivative of such nature. And here we have in all the problems, we can consider nonlinear operators depending on other fractional derivatives. Consider the issue of local solvability for the Cauchy problem to a semilinear equation where -8 generates an analytic semigroup of operators. 0 point belongs to resolving set of A. For applying of the semigroup only, not only for semilinear partial differential equations of this form with nonlinear operator depending on unknown function only, but for equation of this type where the nonlinear part depends on spatial derivatives of the nonlinear function, the fractional powers of the operators, and we will construct fractional powers, but for the fractional order equation. The using of the fractional powers is following. If gamma is between 0 and 1, that gamma is a domain of the fractional power of the operator A with such norm, and we use such condition for the nonlinear operator where this norm in this subspace Z gamma is used, and such construction of these conditions allows to consider equations with nonlinearity depending on spatial derivatives in applications. We will consider a quasilinear equation with some order alpha. It is oldest derivatives, and here we have youngest derivatives under the sign of the nonlinear operator, and maybe integrals. Some of these numbers can be negative, and then we will have integrals here. And these numbers has fractional part of to the fractional part of alpha, but for these numbers, fractional part is equal to this, to the fractional part of alpha of the oldest derivative. And we can define by these numbers, alpha 1 and so on, alpha n, we can define the so-called defect of the Cauchy type problem for the equation with several Riemann-Liouville derivatives. And since our Riemann-Liouville derivatives are under the sign of nonlinear operator, we need to define M with double asterisk as maximum of numbers 0 and M with asterisk plus 1. It is necessary for the existence of the limits of these derivatives at the initial point T0. And then we can consider the incomplete Cauchy type problem of this form for this equation. Excuse me. And we will use this condition of the analogous form to the case of semigroup theory, but with such condition when we will use the norms in these spaces which are fractional powers of the operator A. Denote by this way the sector in the complex plane, and this sector is another complex plane with other variable lambda and tau, and for some theta 0 and a0, and denote by a alpha theta 0 a0, a class of operators linear closed and densely defined in the space Z, such that for every lambda from this sector, the inclusion power alpha belongs to the resolving set of A is valid, and for any theta from this interval and A greater than a0, there exists K such that for all lambda from such sector, we have this estimate. Let alpha belongs to this interval, 0 to minus A belongs to the class A alpha, and 0 point belongs to the resolving set. Then we can, as in the semigroup theory, we can show that resolving set of minus A contains a neighborhood of 0 cut along the negative semi-axis in which the operator function resolving in this point of minus A is bounded. Therefore, for a small a and theta, we have such estimate for the resolvent in the sector with some disk with the center in 0. And then we can construct such contour to axis and the arc and operators. They are fractional complex powers with negative power. We can construct it by this integral. And since in our conditions, we have such inequality, therefore, the integral converges in the operator norm. And then the family of these powers with negative real part of the power forms an analytic semigroup, while for any theta the 0, we have the inequality, the limit, strong limit in the point 0 in such sector is equal to Z0, is equal to identical operator. Excuse me. Let alpha greater than 0 minus A belongs to alpha, 0 point in the resolving set of operator A. Then for real gamma greater than 0, the operator A minus gamma is injective. We proved this assertion, and then we can define the fractional powers of with positive real part of the power as inverse operators for the operators with negative real part, as those operators are bounded, but these operators are defined on such subspaces by the natural way, and we have fractional powers with positive real part, and we also define the operator with 0 power as identical. And for real gamma is equal to 0, we can define by such way the fractional, maybe complex power of the operator with 0 real part. And we prove that this definition doesn't depend on the choice of this beta. And we have such theorem. A gamma is a closed operator for every gamma from complex plane. For real gamma greater than real beta, greater than or equal to 0, we have a domain of A gamma is a subset of domain of A beta. And all the powers of the operator A are dense in the space Z for every real gamma greater than or equal to 0. And we know that if it is not so, then here we have a domain is equal to all the space. And we have the law of the addition of powers. And now we will construct such operators. In our conditions, we can construct such integrals. Here we have a resolvent of the operator minus A in the point mu alpha, and such multiplication by the power function. And these operators has two parameters, t as usual, and beta. Beta is this parameter. Here gamma is a such contour. As briefly, it can be boundary of the sector S theta A. And we have such estimates on the norms of these operators for non-negative beta and for negative beta. And we know that if beta is equal to 0 and alpha is equal to 1, it will be usual semigroup of operators, which is generated by the operator minus A, and which is analytic in a sector containing the positive semi-axis. But now we have, it will be only when alpha is equal to 1 and beta is equal to 0. And this technical theorem contains some generalization of the semigroup property, but this property not for fixed beta, but for all these operators with various beta and delta parameters. And in our conditions for all beta less than 1 and delta less than 1 and TS greater than 0, this composition is equal to such expression with integrals on this contour gamma and with using Mittag-Leffler function with two parameters of this form here. And if we take here alpha is equal to 1, beta and delta to 0, then we obtain the semigroup property, since it will be the left part of this equality. And here we will have minus Z0 s plus t, plus Z0 is plus t, and plus Z0 is plus t once again. And it will be this property when alpha is equal to 1, beta and delta is equal to 0. But this theorem was need for us from the technical reasons, but the result was interesting, not technical. And here we have another technical theorem about the properties, about the estimates for this operator Z beta and such compositions A with Z beta and complex powers A with the then beta and for such expression, and this theorem has technical character, and it is used for the proof of the main theorem. And we will return to our equation and to our incomplete Cassette type problem. Let gamma between 0 and 1, that gamma is domain of A gamma, is a norm space with the norm with such norm. Since A gamma is a continuously invertible closed operator, that gamma is a Banach space, and let U be an open subset of this space. A mapping B is given for all points from U. For all points of U, there exists a neighborhood and constants such that for all points from this neighborhood, we have such inequality. This condition is similar to the condition on nonlinear operator in the analogous problem in the semigroup theory. And firstly, we have the assertion for the linear, inhomogeneous linear equation. Let alpha greater than 0 minus A belong to A alpha. F is continuous with respect to the graph norm of the operator A, or it is a Hölderian function with power gamma in the Hölder condition. Then for all initial values, this function is a unique solution of the Cassette type problem for the linear equation. And we see that using our operators Z with two parameters, we can present the solution of the linear inhomogeneous equation. And we see that it is the solution of the homogeneous equation, but with given initial data. And it is solution of an homogeneous equation with 0 conditions at the initial time. And here we give the solution of the Cassette type problem for nonlinear equation, for this equation and Cassette type problem. And if briefly, it is a classical solution of the problem. It has all the derivatives, fractional derivatives, which are in the equation. We consider we need to continuity all the derivatives which are in the equation. And the argument of the nonlinear operator must belong to the domain of this operator. Theorem on unique solvability of the nonlinear equation. Let alpha is greater than 0, and we have such inequalities. Minus A belongs to A alpha, theta 0, 0. 0 point in the resolving set of the operator A. A mapping satisfy condition, our previous condition, using the norm in the such subspace. Gamma, parameter gamma is greater than this value expressed through the alpha. And this point T0, 0, 0, and so on, and initial data belongs to U, domain of the nonlinear operator, and Zk belongs this subspace, domain of this fractional power of the operator A for such K, as in the incomplete Cauchy type problem. Then for some T1 greater than T0, there exists a unique solution of problem 3031 on this segment. This theorem is about the local uniqueness, the local existence and uniqueness of the solution of the problem. And for the, I will not prove this theorem, but I will talk several words about the proof, about the scheme of the proof. We need such space C alpha, such X, which are continuous on this semi-interval, and this fractional integral of X have to be in this subspace m-1 times continuously differentiable, including the point T0, and m times continuously differentiable, excluding these points. And these product of the power and the last fractional derivative of X must be continuous, including the point T0. And we need the norm, we use the norm in this space of this form, and we proved that it is the norm, and we proved the completeness of this space. It is Banach space, we proved it. Then we take such subspace with zero initial conditions for these fractional powers when K from 0 until m double asterisk minus 1. Fix delta such that the corresponding neighborhood of, excuse me, just a moment. Corresponding neighborhood of this point, in this neighborhood, condition 32 is valid. And we define such set. It is the set of functions from this subspace, such that their values in the points T for all T from T0, T1 is not greater than delta, and some expressions not greater than delta for other K. Then it will be complete metric space for our proof. And in this space, we will show we will consider this operator F for X from F, define a mapping F, and this F almost defined by the formula of the solution of the linear equation, but if we, instead of inhomogeneity, substitute this expression with nonlinear operator. But here we have also a gamma here, and a minus gamma under the sign of nonlinear operator. And in this case, there exists a unique function y from S such that it is a fixed point of this operator. Then a solution of our problem is a function z from this set such that satisfies this equality. In the here y is the fixed point of f in this in the right hand side. Inversely, if function z from this space satisfies equation 33, then this expression, what such form expression, when instead of x we will substitute, excuse me, a gamma z, satisfies the Hölder condition, and that is the solution of 3031. Thus, a function z from this space is a solution of 3031 if and only if y of this form is a fixed point of f, and this fixed point is unique, and thus existence and uniqueness of the solution is proved. Now we can consider initial boundary value problem in a bounded region with a smooth boundary. Initial conditions have such form, and now we have alpha between 0 and 2. So here we have one or two solutions. If not greater than 2, maybe 1, depending on this value. And this is boundary condition, and we have such nonlinear equation. It is nonlinear part of the equation, and it is linear, and it is nonlinear part of the equation, product of fractional derivatives of unknown function v. But with we see that in the right multiplicator we have also derivative with respect to spatial variables xi. And for the reduction of this problem to the abstract problem in the Banach space, we take z is equal to Lebesgue space. A is minus Laplace operator with such domain which includes the boundary condition. Then minus A, it is known, belongs to this class. It is proved previously. For in the case when alpha from 1 and 2, obtain the nonlinear operators of this form. This is the form is the same as here in the equation, nonlinear operator, but instead of fractional derivatives, we use arguments of the nonlinear operator. Then it is known, and it is shown in the, for example, in the monograph of Pazzi. This operator satisfies the condition of theorem 6 at gamma greater than 3 divided by 4. And I recall that gamma in our theorem is using in the, just a moment, in the condition here we use gamma. And in our theorem, we consider the case when operator B satisfies condition gamma and gamma greater than 1 minus and thus, due our theorem for all Vk from this domain and for all this K, there exists a unique solution of problem 3436 in cylinder with some T1, with T1 sufficiently close to T0. And for semigroup theory, analogous theorem is proved, for example, in the monograph of Pazzi, semigroups of linear operators and applications of partial differential equations. In these works of me and my students, we proved in these two works, we proved the theorem of the unique solvability of the inhomogeneous linear equation, but with other inhomogeneity, with continuous in the graph norm and with Hölderian. And here, this paper, which is published recently, contains the main result of my report, of my today talk, and other works of our group. For example, this work is about the multi-term equations with Riemann-Liouville derivatives. Thank you very much for your attention. I'm ready to respond.
Thank you for a very nice talk. Questions, please. You finished before the time, so you have a lot of time for discussion. Questions? Okay, then I have a question. From your point of view, which result you consider the most important and interesting in that talk?
I think that the main result of this talk is the theorem on the unique solvability, local unique solvability of this theorem, since as I talked before, it allows to study initial boundary value problems for partial differential equations or systems of partial differential equations with nonlinearity, which depends not only on unknown function, but also over partial derivatives of these functions, or maybe functions. I think so.
More questions?
Выполнено внесение исправлений.
No questions. So let us thank the speaker again.
Thank you very much.